Hi, everybody. Just a second, we'll set everything up. Okay, we've set everything up. Hi. I'm Eric. I am the VP of Technology, lead the research at Fireblocks. I'm gonna be talking really fast because I'm trying to dense like what should have probably been a 40-minute talk to 20 minutes. But I can talk fast, which is good for this. The first question is, why am I speaking about MPC at internet scale? And there's two parts to the answer. The first part is because obviously I work for Fireblocks. We at Fireblocks use MPC as part of our offering to help institutions, companies to use the blockchain or to build on top of the blockchain at very high scale. So far, we've processed more than $10 trillion across our system. MPC is very important for us in securing clients' assets. The second part of why I'm talking is because I believe cryptography is too important to leave it to only cryptographers. Now, obviously, we need a lot of cryptographers here, but I think that actually the combination with architecture is very important. And a lot of this talk is going to be on those edges of where cryptography meets architecture and what does it mean and what we can take from that to create new solutions. And I'm not a cryptographer. Great. Okay, so we're going to do this in a few chapters. The first one will be short, the last one will be longer, and we'll get to, hopefully, on time, where we want to get to. The first chapter is ECDSA. Why do we use ECDSA? And the reason we use ECDSA is because Schnorr is patented, or was patented, right? So Schnorr was invented, amazing, fast, easy, MPC friendly, all of the great characteristic, but with a really strong patent on the actual cryptography and a lot of different ways of using the cryptography. And the result is that a lot of people that were deciding what they use could not choose Schnorr because like the patent was just too strong. Obviously, ECDSA was born to basically give an alternative. And so we see ECDSA embedded in a lot of technologies that are not easily replaceable, right? If you embed ECDSA in a hardware device, as long as the hardware device lives, you cannot really take it out. You need to support it, and the systems on top of it need to support it. There's a great lecture. Actually, I'll get into this in a second. But basically, like it's being used in a lot of different places beyond blockchains, right? A lot of places beyond blockchains. I'm not sure if people know iMessage uses ECDSA internally. Digital certificates today use ECDSA. So it's really used in a lot of places. It basically became like the RSA alternative. Right? If you don't want to do RSA because all of the bad things that we all know about RSA, and you want an elliptic curve solution, you go with ECDSA. And that's how it's embedded in a lot of places. So basically, Schnorr for ECDSA is a bit of like the VHS moment, right? It's not just about the technology that's a bit better, it's more about the technology that's already entrenched. So if we want to take one thing from this, ECDSA is here to stay. And again, I was about to mention there's a great lecture by Abi Shalat about this specifically, about the entrenchment of cryptography in different places. It's worth a watch from The Compute a couple of years ago. Great. Okay, so we have ECDSA. Now let's talk about MPC. So why MPC? So obviously, like I'm not going to do like an entire MPC 101. I'm assuming a lot of people here are familiar, but basically we're talking about multi-party computation, the ability to compute something with multiple parties involved in a way that does not disclose the secret information, which could be a cryptographic key. Now, I'm going to categorize MPC. Obviously, there's different ways to categorize, but I'm going to use specific ones. So we're going to be talking about MPC versus 2PC. Either multi-party or just limited to two parties because it has specific characteristics. We're going to be talking about honest majority versus malicious security. So this is like, if I run the MPC process, how sure can I be that the eventual result is correct? And general purpose versus specifically threshold signatures, which is most relevant in digital signatures in our space. Okay, so why have blockchains been so prominent? And like I wrote there, like it's the product market fit moment for MPC was in blockchains and blockchain wallets specifically is because of three things. Okay, it's not a lot, it's not very complex. We have three things. Number one, no single point of failure. Everybody always talk the key, the passphrase, single point of failure, single point of failure. We solve that with MPC, right? We have multiple devices holding parts of the key, no longer single place. That's great. That's very important. So you cannot just steal a key from one device and get the money. You have to now hack multiple devices. Number two is self-custody. Right now, obviously, self-custody is more regulation term, not a technology term, but the implication is basically that the user has the control, right? And again, if the user has part of the key, they have a lot of the control. You can do backup so that they have access to other parts of the key, but eventually you cannot sign without them. So as a malicious provider, we cannot move money around in any case, right? So like it solves the problem of malicious providers, but also it solves the problem of not a malicious, but like a compromised client. So if your mobile device was hacked, again, somebody can protect you. If you're trying to sign something you didn't want to sign, somebody can protect you. I call it server oversight. And the policies can depend by your use case. Okay. So we understand we have ECDSA, that's useful. We understand we have MPC, that's useful. Now let's talk about the combination. So the combination of MPC on ECDSA, like is an entire field. And so when we have this kind of field, multiple protocols, multiple solutions, the question is, how do you decide which solution is good, right? How do you measure? How do you compare? You need to have something standardized or at least like similar. So there's a few things that most papers talk about. We talk about communication and we talk about scalability. In communication specifically, there's two things. How many rounds of interaction do we need to sign? Because MPC is an interactive protocol. There's going to be some iterations between the parties. So how many rounds? How big is the message? That is the communication part. When we talk about scalability, there's new things. How much compute do I need? How much memory do I need? But that's all focused on one machine. We're going to also add in this conversation multiple machines, which is not a highly talked about topic in the space until now. Okay. Now, MPC CDSA is really hard. How do we know it's hard? We're going to compare it to Schnorr again. So the first Schnorr solutions, like to do MPC on Schnorr, 3 rounds, highly efficient, right? That's like, we call it classic Schnorr. I'm not sure everybody calls it like that. But like, Schnorr is MPC friendly. Like any cryptographer looking at Schnorr says, I know how to MPC this, it shouldn't be very hard. ECDSA is not. So people have been working on it really, really hard. The first solutions required 8, 9 rounds. I think there were even like 11, 12 round solution initially. But then like people were working and working and working to make it better. But there is a bit of a stigma saying like MPC ECDSA is slow. So like I hope we break that stigma today. But yeah, this is kind of like nobody was thought it's fast and efficient in the past. So here's a bit of a comparison of a few protocols. You can see most of them are quite recent, 23, 24 mostly. And you see there's improvement, right? So like, again, you can see kind of like the reds indicates not good things and then the blue indicates better things. And you can see that we have more blue lines coming up recently, which is good, right? But we think this line is the best. And this is the last protocol we released. We call it BAM internally. And it's really fast. And it has a few characteristics that we like, not just speed. We'll be talking about this. And there's obviously a lot of things in parallel to other protocols. Okay. So we talked a bit about, like, we covered some of the base cryptography things we need to know for the architecture conversation. Finally, we get there. So how do we bring architecture into a cryptography discussion? So let's talk about the high-level architecture of a wallet, because again, that's the space we come from. You have a provider, maybe a wallet provider or some provider, and they send a signing request to the user. The user gets that request, and then if they want to do signing, we start a signing process. How much of a process? We'll talk about this. But we have a signing process, and then eventually there's a result. The server gets the result, sends it to the node, to the blockchain. You know, that's like very simplistic architecture. Now, let's categorize the MPC protocols. What do we choose for this architecture? And I'm not talking about Fireblocks right now. I'm talking about generic. Don't assume everything here into Fireblocks. So first of all, we can obviously do this general purpose MPC, but TSS is more efficient for signatures. So there doesn't make sense to do general purpose for this. We're going to take TSS as the base case. We can do MPC. But actually, we only have two parties communicating, so maybe 2PC is enough. We can do MPC if we want like additional assurances, but actually we can also do, for the people familiar, we can do 2PC where one of the parties is actually a virtualized party for another MPC. So if you want more players involved, you can do that with 2PC as well. So 2PC is faster, more efficient solution for a two-person problem. So we're going to use 2PC for this conversation. And the last one, obviously, there is no majority between two. So like honest majority doesn't really make sense here. It's also important for us to protect each party from the other party. I mentioned this. So malicious security is what we go for, so that each signing key is as important as any other in this and has to be included fully in the solution. Okay, great. So let's start talking about communication. I said it's going to be fast, right? It's like, okay, let's start talking about communication. Rounds. Rounds are important. I'm going to prove it to you, okay? I'm not sure if you remember, but some of the slides before we're talking about time of computation, some protocols like write 4 milliseconds or 10 milliseconds, 20, 50, 80, but then you add one round and it can be 300 milliseconds added. So if you have four rounds on a 1 millisecond protocol, well, we're talking about more than a second, right? So like rounds are really, really, really important. I hope you remember this. Rounds are really, really, really important because a lot of the latency just comes from communicating. By the way, this is from a DKLS paper, not ours. And this was measured between servers in a Google server farm, right? So like, this is not like the guy in the desert on their phone. This is like a Google server talking to a Google server. If you try to measure it in other conditions, you might get much, much worse results. Okay, so rounds are important for speed, but also rounds are really confusing because I think about rounds like this. Oh, I sent you a message. That's like a round of communication, right? And you sent me a message. Now it's 2 rounds of communication. But rounds are also, I sent you a message and you sent me a message, but it happened at the same time. I don't know what the same time means in architecture. I understand it means something in cryptography, but in like, what does it mean? The same time. But actually, when somebody says, I have a 2-round protocol, you should ask him, so how many messages do you pass? Is it like 2, 3, 4? Like it doesn't say that, right? So because rounds in cryptography are a bit confusing. But in architecture, we need to know what kind of rounds it is. So when we talk about architecture and you try to combine this entire thing into one, I'm going to say that what we have is what we see on the left side, right? We have a signing request, some signing process, and then a result. What we want for scalability is the right side. What we want is to not add any messages on top of the one message that the client has to return to the server to continue executing. That is optimal architecture for what we want in terms of scale. Now, what do I like about this as architecture? If you're an architect, you've built internet system, this architecture should look very familiar. You're like, server sends notification to the mobile device does something, returns answer to server, executed. Provider sends webhook to API user. The API user analyzes this, does something, right? Like we know this. This is like, I call this like the internet architecture. It's like a push notification, action, return back to client, execute, return back to server, execute. So this is what I want. I want internet architecture. I don't want like this MPC architecture. Now to do this, I would want a 1-round MPC protocol. But there is no 1-round MPC protocol. If you looked at the table, like it's right now, we don't think it's possible. Hopefully someday, will we call it MPC still? But the ones we have are 2-round MPC protocols. But we want the good 2 rounds. We want 2 rounds that are actually 2 unidirectional rounds, right? So like send from server to client, send back, execute. That's the kind of MPC we want for this picture to happen, for it to actually be the kind of architecture that we want. Because what we hide here, that we can actually piggyback on the signing request, maybe, right? In some situations, maybe we can piggyback on the signing requests to start executing. Now, any additional round that you need to do, that's a lot of time, right? That breaks the architecture. Like it's no longer this architecture that I want. So we really like the 2-round protocols for this architecture problem, right? And there's a few. in this table. This is only CDSA ones, but there's a few. Our work is obviously one of them, BGLS 24 as well. They're all very recent, but they actually do this. Now let's go a bit further. Okay, message sizes. So again, generally speaking, in cryptography, we don't really care about the message size. It's just a parameter, right, like that we write in the paper. But in real world, sometimes message size is limited. I'm not even talking about just more size of message takes more time, which is obviously the case, right? Especially if you're like a remote connection, you're not like on 5G. But I'm not even talking about that. A push notification is limited in size. A push notification can only do 4 to 5 kilobytes, both in Google and in Apple. So if you have more than 5 kilobytes, that doesn't go through a push notification. QR codes, limited, 3 kilobytes. If you have more than that, doesn't go through push notification. If you have like 100 kilobytes of message, you need to pass in a QR code. Like you're gonna start doing like this with the QRs all the time. That's not fun. Okay, so like message sizes are actually also important. To some extent, message size equals possibly more rounds, right? So we really want small message sizes, and I think you see where that's going to. So it was really important for us because we're not doing this research just generally. We do this for a specific architecture. For specific solutions, we need small message sizes. We use QR codes. That's important. Obviously, mobile devices. Okay, so you understand why I really like our solution because of the architectural implications of it, right? Not just like the cryptography. And this kind of summarizes the entire communication, right? I call this architecture costs. So you have the cryptographic paper, you have the costs that we describe in the cryptographic paper, but when we overlay it with an architecture, we might add more rounds, we might add more costs. If we have to do this, suddenly like protocols that might look really good for some use cases will not look good for other use cases. And again, this really depends on what you're building. I'm not saying it's bad, but in some situations, it does impact your entire architecture. Yeah, we talked about this. Sorry. Okay, so we understand communication. We understand what we care about in communication. Now let's talk about scalability. Optimizing the scalability of a single server is just not enough. Okay, like the solution to a lot of problems in the MPC space is get a bigger server. Okay, but eventually, first of all, it's very expensive because like getting really big servers is expensive. But eventually, there is a limit to how much you can scale. You cannot scale indefinitely with adding a big, like just making your server bigger. You need to go multi-server. Okay. So what does internet scalability usually look like? It looks something like this. The provider has one server sending you the first message. You do your thing. You send it back to a different server. If you can describe internet scalability in a nutshell, this is it. Okay? Because if you do this, I can now build a bunch of servers. Now, I'll introduce something because again, like if you build architectures, you know that the way to get to the thing I described is stateless services. Usually, there's other ways, there's a lot of things, but stateless is like the gold standard, right? So let's define stateless in the context of MPC. The way we define it is anything generated in the key generation process is not state, it's storage. Because we know how to synchronize storage. That's not a big problem. But anything created during the signing process, so in the immediate interaction, that is state. Okay? And what we want is an MPC process that does not have state. Now that is easier the less rounds you have because you need to keep state between rounds. So if you have very few rounds, easier to keep state than if you have a lot of rounds. Or at least it's easier to not have state because you basically need to find some way to not have state. Now, obviously, if you do have state, there's a problem. Because what you need to do, you need to start synchronizing the servers because they have state. And if you go to a different server, you need to do one of two things. Either you're sticky, so you started from one server, you always return to the same server, or you need to synchronize servers. The problem is if you don't, it's not like a scalability issue, it's a security issue. Because if you don't synchronize servers, that's actually a security risk. So that entire thing makes scaling hard. So let's do a naive attempt at solving this problem. So I have two suggestions. One is we're going to have a database. And we have 2 servers, 3 servers, 5 servers, 9 servers. But they all work with the same database to get the state, right? That's That's a reasonable architecture idea. And the other one is we're going to actually piggyback on the protocol. So I know I have state, and I'm not sure you're going to return to me. So I'm going to encrypt the state on the message so that when you get to the other server, you send the state with the message, right? Make sense? I'm going to be piggybacking on the messaging to pass state between servers. Now, there's a small problem with those solutions. The problem is they're all hackable. They don't survive. They don't work. Now, why are they hackable? They're basically vulnerable to enhanced reuse. The reason is, and this is a result of my dog, is that just because I said the dog should go through the door does not mean the dog will go through the door, right? It can go through whatever it can go through. So just because I said that if you are supposed to do something doesn't mean you will do this. So a malicious user in this situation where I have two servers trying to interact with them, a malicious user will try to play a game and somehow to get two different servers to sign on the same payload with different randomness. Okay, or there's some permutation to this attack, right? There's different ways to do this. But if somehow we can do this, we get the key because we can craft randomness that will steal the key. So if we have two servers, they have communication, but suddenly there was a small disconnect between them for a second. If I was at the right second, I will get the key. If it was like encrypting the message, I don't even need to be fast. I have all of the information to devise the attack. Right? Like I don't even need to try hard. So like basically the sync between the servers becomes so critical that I do not get scalability. Because if you get to a different server, they need to check that they're not doing something in parallel to another server. If you have a lot of servers, all of them need, it just doesn't, like, it's not good. Okay, this doesn't work, this will be hacked. So we will state that basically, or will suggest that basically to get scalable MPC, you need stateless MPC. Okay, because if you have state, the problem is just too risky, it's just too hard. So like if you want to scale to many servers, you need stateless MPC. And a way to achieve that is deterministic MPC. Okay, so that not that you need to move state around, but actually that the protocol works in a deterministic way to create good outcomes. Now, there has been some really great progress around this. So like, let's talk about what's been done. So first of all, we talked about the first part, right? We need protocols that are very efficient in the round complexity. We call it optimal round complexity. So they have two unidirectional rounds. We have BAM, which is the protocol that we published. It's a nickname. We have BHLS, which is a protocol that was published just before that. And we have Frost for EDDSA. Okay, so we have three protocols that have the characteristics we are talking about, that two unidirectional rounds. Obviously, they have different characteristics in terms of compute, in security assumption, in other things, but that's already preference of like the protocol and other things. But the other thing we need is basically deterministic randomness. I want the client to not be able to choose randomness to attack me, right? Because that's the problem. So there's a new gadget introduced in the BHLS paper called EVRF. And that actually solves exactly that problem, okay? What EVRF allows you is to have the client be forced on the protocol level to create deterministic randomness. Not going to go into the details of it. If you want to go to the details of it, Yehuda Lindell, one of the authors of that paper, did a great presentation for A16Z describing this. Very understandable for anybody from the space. Now we have our own version of a EVRF in a new paper we're publishing, but again, that goes into specific mechanics and architectural choices. But basically, the combination of those things basically mitigates the attack. So now that you have that protocol and you have that gadget, you get what we want, which is internet scale MPC. Because what we can do now is we can have horizontal scalability. We can have as many servers as we want. More clients joined, get more servers. We couldn't do that in the past, right? This is very big. We have high availability. We have disaster recovery. There's a lot of the nice stuff we get that eventually equal internet scale capabilities. And this can be used beyond blockchains. Blockchain signing, passkeys, identity. There's a lot of places where ECDSA is being used. Hopefully, we see MPC going into all of them. Thank you very much. A lot of great people worked on this, and obviously we stand on the shoulders of giants in research. Thank you.